excellent. Good, good. Okay, I think I might as well go ahead and get started. Yeah, okay, so welcome back. Haven't done one of these in a while. And if this is the first one that you're seeing, welcome. So, okay. In the last one of these, if you were there or if you watched the video or whatever, you'll remember that we talked about Fourier series. And specifically, we talked about it in the context of solutions to the wave equation. And the Fourier series came up as a solution to the wave equation with specific boundary conditions. And then what we found was that when we relaxed those boundary conditions, we got a sort of generalization of that Fourier series, which we called the Fourier transform. And so that's what I really want to talk about today. I want to talk about the Fourier transform, and I want to talk about it, both in and outside of the context of the wave equation, because it has a vast number of applications, specifically using it as a tool for solving differential equations. That's usually the main context that you see Fourier transforms in. And so that's going to sort of be the main focus of what I'm talking about today, is using these Fourier transforms as a tool for solving, differential equations that we see in physics. And then I'll sort of get into talking about, the types of integrals that might show up in this, how we go about solving them. And the last thing that we'll sort of talk about is a very specific case where something, some people have seen it, some people haven't. We see this idea of an uncertainty principle show up, where if you're at all familiar with quantum mechanics, you've probably heard of these Heisenberg uncertainty principles. But what we'll see is that it's not anything special to quantum mechanics. It's just something that is inherent to this sort of Fourier analysis. Okay, and so with that, let's go ahead and get started. And of course, as always, if you have any questions, please feel free to leave them in the chat. I'll try to get to them in a timely manner. Okay, so the first thing that I want to do is I want to write down what a Fourier transform actually is, and it's just a mathematical relation. So Fourier transform. So we have two pieces to it. We have the Fourier transform and the inverse Fourier transform. It doesn't necessarily matter which one you call the Fourier transform and which one you call the inverse. But there's essentially, we get two variables. One I'll call x, and the other I'll call k. And these are our Fourier transform pair. This FT pair. And just the idea behind the Fourier transform, again, I'm taking this all out of context from the wave equation. We saw how it showed up in the wave equation, but this is sort of just the mathematical, this is what a Fourier transform does. It relates functions, so functions of x, and it relates them to different functions of k. So I'll typically call the Fourier transformed functions, I'll give them a tilde, but it's just some different function that takes this k as an argument rather than x. And the Fourier transform itself is just this relation. It's done via an integral, k f tilde a e to the I kx. And then we also have to specify the inverse, which is 1/2 pi minus infinity to infinity, whoops, dx, f of x, e to the minus I k. And these are our Fourier transforms. Or, okay, so this is the Fourier, I'll call this the Fourier transform, call this the inverse Fourier transform. This isn't the only way to define them. I'll say that right now. Sometimes you might see the 1 over 2 pi over here. Sometimes you might see something like a 1 over square root of 2 pi in both sides. It doesn't. There's not one definition of a Fourier transform. This is the definition that I'll use. But the important thing is that you have essentially an overall factor of 2 pi. And the reason is so that you get this Dirac delta function relation. Right, so if you remember back to the last stream, if you saw it, we found that we could define this Dirac delta function like this. Infinity to infinity, dk e to the I k x minus y. And what this function does, okay, I use the term function loosely. Technically, it's not a true function, it's a distribution if you want to be super technical about it. But regardless, what this does is it takes an integral like this, f of x delta x minus y equals f of y. And it essentially picks out a single point in this function and evaluates the function at that point. Essentially what it is it's the generalization of this Kronecker delta to a continuous variable instead of a discrete variable. But so this is why this overall factor of 2 pi is important, because essentially if I Fourier transform and then I do the inverse Fourier transform, I better get something which looks like this relation. Okay. So that was sort of the lightning review of what we found the last time. So these are our Fourier transforms in our Dirac delta functions. So now, how do we use this? How do we actually go about using this as a tool, right? These are mathematical relations, fine, who cares? So there's sort of like this classic example for introducing these ideas of Fourier analysis, and it's known as the damped harmonic oscillator, or the damped driven harmonic oscillator. And so I'm going to be talking a lot about that system today, just because it provides a very nice, neat context for all of this. That's not the only system it's applicable for, but it's a very nice one to look at. Okay? So the setup for the damped-driven harmonic oscillator is something like this. So up here, damped driven harmonic oscillator. And okay, so the setup looks like this. It's a standard harmonic oscillator, right? So I might attach it to like a wall or something. Say I'm attaching a spring or a mass to a spring over here. Give it mass m. Give the spring some spring constant k. But I'm also going to include what people typically call a dash pot on this. And it'll have some characteristic damping of beta. And what this damping essentially means is that I have some sort of resistance in my system. Specifically, I'll say that there's some, it acts as like a frictional force. So I'll write this F sub F f of t. And this is going to be acting in the opposite direction of the velocity of this thing. So it has some constant beta. And the force just acts in the opposite direction of the velocity, but it's proportional to the velocity. So the faster this thing is moving, the more of a frictional force this is going to feel. And this is typically called a damping force. Okay. We know that from a spring, so the force that this is going to feel from the spring is just going to be minus kx of t. And then we'll also say we'll allow some external driving force. So maybe we have it attached to a string and we're pulling on this string or something along those lines. Or maybe it's hanging in a gravitational field, or maybe it's a charged mass and we put it in an electromagnetic field. Whatever it may be, we're going to say that we're going to allow some driving force Fd. Okay, so the very first thing we need to do is write down a differential equation that describes this system. Right? We drew our picture. We have all the forces involved, so now we need to write down our differential equation, which we can do just using Newton's second law. So we know that the total force is just going to be the sum of all of the forces that this thing feels. So it's going to feel the force from the spring, it's going to feel our damping force, and it's also going to feel our driving force. And we also know that from Newton's second law, this is equal to ma, the mass times the acceleration. Now, I'm going to introduce a bit of shorthand. I can't remember if I did it on the last stream or not, but it's just a bit of a shorthand notation. And the shorthand notation is that I'm going to denote a time derivative by a dot. So if I'm taking the time derivative of x, I'm going to say it's x dot. If I have d2x, if I'm taking a second derivative, this will be x double dot, so on. It just makes things a lot cleaner to look at. Hopefully that doesn't create any confusion or anything. So in this notation, I can rewrite this as minus kx minus beta x dot from this term, plus whatever this damping force is, and this is mx double dot. Just to make life a little bit easier, I'm going to rearrange this and get a nice differential equation plus beta x dot plus kx is equal to whatever my driving force is. And this here is the differential equation that I want to solve. Okay, so this looks like a hard differential equation, right? It's a second order differential equation which has some first derivative, it has second derivatives, has arbitrary constants out front. So this, in principle, is going to be a more challenging differential equation to solve. So let's look at what happens if we try to Fourier transform all of this. And so when we do that, we're going to say that we're going to call our Fourier transform pair instead of x and k. We'll say I'll call it t and omega. This is just my Fourier transform pair. So that I can write x of t is equal to this integral k x tilde oops, not k. Just said we're not using k. The omega e to the I omega t. And then the other thing I have to know is the driving force. But again, I just get a similar relation here. F tilde the omega e to the I omega t. Okay. Now we want to prove a very interesting result, a very, very, very useful result. And that is, what is the Fourier transform of a derivative? So if I want to do a Fourier transform of x dot t, what does that look like over on this side? Well, it's actually pretty straightforward to do. This is just the time derivative of this integral e omega x tilde omega e to the I omega t. So this integral only ever sees omega. It couldn't care less about t, right? It's only going to act on omega, which means that I can push this time derivative. This time derivative also, in a similar way, doesn't care about omega. You can do whatever you want with omega. The time derivative is not going to care. It's only going to care about what you do with the time. So I can push this time derivative past the integral. I can push it past x tilde, because x tilde doesn't depend on t, so the time derivative is going to completely ignore it. And it's just going to act on this exponential. When it does that, it just brings down a factor of I times omega. So this is just that. So on the left-hand side, I have a time derivative. On the right-hand side, I've just brought down a factor of I omega from the integral. And so, we can invert all of this, and what we'll see is that I omega x tilde of omega is 1 over 2 pi the x dot of t e to the minus I omega t. So essentially, with all this said, and so you can do it a different way from starting from here, and then use integration by parts or product rule, whatever you want to call it, and backtrack the same result out. But so the important result is that when I have, so say I have a time derivative of function, and I Fourier transform it, that just becomes I omega times that function. And now, when I'm looking at the dual variable, so in this case, if I have the f tilde, the omega, and I make a Fourier transform, I get a minus it f of t. Just because this exponential here has the minus sign out front of it. So which one has the minus sign and which one doesn't isn't as important as the fact that one has a minus sign and the other does not have the minus sign. Similar to where this factor of 1 over 2 pi goes. One of them must have a minus sign, one of them must not have a minus sign. Where you put it isn't particularly important, but you see that it makes a difference here. So this is a very important result, and something definitely to keep in mind when we're doing these Fourier transforms. And immediately you see how this might be very useful. Because when I go back up to this differential equation here, I have these time derivatives, sure. And okay, so let me rewrite my differential equation down here. Mx double dot beta x dot plus ax equals ft of t. And now I'm just going to Fourier transform everything. Or I suppose more accurately, I'm going to write it in terms of the Fourier transform pair. I'm just writing all of these x of t's and all that stuff in as these integrals instead. And what I find is a minus m omega squared, because I get two derivatives here, so I get an I squared times omega squared, plus I beta omega, and then just plus k times x tilde omega, and that is equal to this guy here. Oops, got the exponentials. Bad. Pi omega t omega f tilde d omega e to the I omega. Okay, so now what we can essentially do is we can basically just drop these integrals and the exponentials, because I mean that's the same on both sides of the equation. Another way of seeing it is you can just do the Fourier transform on both sides and it'll get rid of all of the integrals and exponentials and all that stuff. And we'll just be left now with this nice algebraic equation. Tilde omega is equal to f tilde d omega. And here we see the magic of Fourier transforms, what Fourier transforms really do for us when it comes to differential equations. And it's that they turn differential equations, which are notoriously difficult to solve in general, into algebraic equations like this, which are much, much more straightforward, much easier to solve. So this is why Fourier transforms come up so often when we talk about differential equations. This exact reason is it just makes them easier to solve as a tool. So now that we have that, I'm going to take a quick pause, see if there's any questions. I see somebody saying they doubt that something is legal. Which part are you concerned about? Maybe it wasn't that concerned. But yeah, if anybody else has any pressing questions, you'd ask. Oh, swapping the derivative with the integral. Yeah, okay, that's a good thing to talk about probably, because what? Sorry, let me think about how best to say that. So when I look at this, swapping the derivative in the integral, like I said, the time derivative doesn't care about omega, right? It sees omega as a constant. Anything happening with omega is going to be a constant. So where is all of the time dependence? All of the time dependence is tied up in here. In this e here. So when I do this integral likewise doesn't ever see this factor of t. So if I take the derivative first, or if I take the derivative next, it doesn't really do anything. It doesn't change anything. In a similar way, if I do d dy df dx, this is going to be exactly the same as if I take the derivative on y first, and then take the derivative of x. They're two completely different variables, so they essentially completely ignore each other. So I can mess around with one of the variables as long as I'm not touching the other one, and it's all totally fine. Obviously, there's much more mathematically rigorous way of showing that this is true, but in sort of the more hand-wavy, I'll say physicist way of talking about this, the time derivative, it really doesn't care about what you do with omega. And if that does really bother you still, there's a different way to prove this relation starting from here, just doing the Fourier transform of the time derivative, where you can do, this shouldn't be x, this integration by parts, and essentially move the derivative off of this x, push it onto the exponential, and you get this exact same relation. But I will just say that this shouldn't bother you. This is a completely okay thing to do. Okay. Okay. So we'll go ahead and move on. Okay, so when we do this Fourier transform, what's it actually telling us? Specifically in this case, yeah, I agree that this is much easier. All this talk of which thing comes first, the integral derivative, whatever, what ignores what. It is much easier to understand if you look at things in terms of these limits and all that. But I don't want to get too sidetracked from this. Yeah, but it will be much clearer if you look at it in terms of the limiting behavior and all that stuff. But okay, anyway, so what is this Fourier transform actually doing for us? So when I look at this, I see, in my Fourier transform, I have something like this, an exponential. And I know that the argument of an exponential should always be unitless. It should be dimensionless. So this automatically tells me that whatever units omega they have to be the inverse of whatever units the time variable has. And this, 1/seconds, this is what we typically call a frequency. Just looking at units, right? So if I have something which is like 1/seconds, this is typically called a hertz. But this is a frequency. So what this is really telling me, so if I find x tilde of omega, this is actually telling me what frequencies contribute to the motion. Motion of the mass. So when we solve for omega here, that's what we're finding. We're finding which frequencies that we eventually add up to give us our solution. If we think back to what we did with the Fourier series, we talked about them as essentially basis functions. And so this is essentially just telling us which of those basis functions we're keeping and which of those basis functions we're not. It's a little bit more difficult to think of here because there's not a discrete set this is all continuous, but the same principles apply. But just to sort of show you a more explicit case, let's think of the case that we're very familiar with by now, where we don't have any damping and we don't have a driving force. So we're going to set beta equals to 0 and f sub d equals to 0. We have no driving force, no damping, just a regular harmonic oscillator. So in that case, we get something which looks like omega plus k x tilde omega. And that's equal to 0, right? That's just taking this equation here, plugging beta to 0, plugging f tilde d equals to 0, right? Because if I make the driving force 0, then obviously f tilde is also 0. That's the only way this integral is going to work out. But so I get this equation, which is easy to solve, right? It's just I take this piece here, since x tilde should be allowed to be arbitrary, then this is the part that has to satisfy. This is the part that has to be 0, and I get that omega squared is equal to k over m, and so we get two solutions, square root of k over m, right? Okay, this is, this is what we expect, though. This is what we always find when we solve the harmonic oscillator. We just found it very quickly here. We didn't have to guess a solution, take derivatives, any of that stuff. All we did was we Fourier transformed, and it just has to be these solutions. So then, so these are our, right, this is exactly what we find for just this differential equation. If I guess x of t equals, I don't know, a cosine omega t equals b sine omega t. This is exactly what we find. But so now I can choose a form of x so that I essentially only pick out these two solutions, right? So I can choose x tilde omega equals some constant, which I'll call a, not necessarily the same a as this, but omega minus omega plus b delta omega minus omega minus. So you see that this is only going to pick out one of these two solutions, and we're good. This solves this algebraic equation. Okay, so going back to our interpretation of what this Fourier transform actually tells us, if I were to plot this, I essentially just get, here I'll say this is minus, or I guess omega minus, omega plus, and I get these delta functions, which we know are these just infinite points, essentially. These are points only defined at one value, but the actual value of the delta function at that point is infinity. So, but here we see exactly what I was saying earlier. This x tilde is telling us which frequencies actually contribute to the motion of our mass. Here we see there's only two frequencies which contribute, which of course we already knew, which is this omega plus and omega minus. So when I plot something in omega space, that's what I'm plotting, just to sort of drive that point home. Okay. Oh, thank you. That's very kind. Yeah. Okay. So now let's look at a more interesting case, where we do have a damping force. So we'll say beta is not equal to 0, Um, um, so, okay. Oh, saw a message, or I saw a question and then it went away. So, okay, I think the question is essentially like, when are you allowed to do this? And sort of to not dive into a super deep discussion, I'll sort of leave it as when these integrals are well behaved, or when the functions are well behaved with respect to these integrals. So I think you said square integrable. I think that's correct, the correct way of saying it. But at the end of the day, if the integrals blow up, then I can't do this. If they don't, then this is typically an okay thing to do. I'm sure there's plenty of counterexamples to what I just said, but in the grand scheme of things, as long as the integrals are, well behaved, well defined, all of that good stuff, this is all okay. And this is sort of the danger of talking about the delta function as a function instead of a distribution and all this stuff. It gets very, very technical very quickly. But so that's sort of the thing to keep in mind. But that I again can't see the question anymore, but I think it was a very good question. But okay, anyway. So let's look at the case where beta doesn't equal 0. So we have some non-zero driving force. So beta not equals 0. We'll keep the driving force equal to 0 at this point. But we'll also restrict ourselves to the special case where beta is less than 2 square root of km. The reason why we're going to restrict ourselves to this case, we'll see shortly. But this is just a restriction that we'll have for right now. So this is just the damped harmonic oscillator, undriven harmonic oscillator. So in this case, my equation looks something like this, plus k, x tilde omega equals 0. So again, I can't, or I don't want to just set x tilde equal to 0. So I know that this all has to be 0. And of course I can solve this with our favorite quadratic formula. And naturally we get two solutions, which I'll call omega plus and omega minus. And this looks something like beta for km minus beta squared all over 2m. And now you see why we want to make this restriction, so that essentially this square root term is always real. So the argument of the square root we want to be positive for the time being. We'll look at the case later where it's not. But for the time being, we'll look at this. And I mean, things look more complicated, all that stuff, but it's the same thing that we just did. So we can essentially just define our x tilde to pick out just these values of omega plus beta delta omega minus, and there we go. We have a solution for x tilde which satisfies this equation. But we want the motion. We want the motion of this thing. So what we can do is we now just plug this into our Fourier transform, right? We know that, I'll write it up here, x of t is equal to this integral e omega x tilde omega e to the I omega t. And so this is actually very nice because, well, delta functions are super convenient to have when you're integrating. So we have this term here, e to the I omega t plus b integral minus infinity d omega minus omega minus e to the I omega t. And now we just use this very nice property of delta functions that picks out a solution, this single value of omega. So we get two terms, e to the I omega plus t plus b e to the I omega minus t. Okay? I'm going to come down here and rewrite this. Equals a e to the I omega plus t, b e I omega minus t, or omega plus minus. And actually, I'm going to rewrite omega plus minus now. I'm going to write it as I gamma plus or minus, and I'll call this big omega, where gamma is equal to beta over 2m, and big omega is this square root term. Squared, whoops, 4km minus beta squared over 2m. Okay, so now we can just plug this stuff in, and we find, so both terms here, so this first term here with the factor of I times gamma, it doesn't change between omega plus and omega minus. So I'm going to pull that overall factor out. And I'm going to use, obviously, I squared equals minus 1. So this I times this I is going to give me a minus gamma t times a e to the I big omega t plus b e to the minus I big omega t. Because that's the only difference between omega plus and omega minus, is the sign of this omega term. Now I can just rewrite my complex exponentials in terms of sines and cosines to make what's happening a little more clear. And I get some new constants, a cosine omega t plus b sine omega t. And there we go. We have our solution. What is this describing? Well, we have our usual harmonic motion, right? This just our oscillating. Okay, we have our sines and cosines, which just give us the standard oscillation that we would expect from harmonic motion. But we also get this term out front. And this is what comes from the damping. And it's this exponential decay. So as time goes on, the amplitude of the oscillations is going to decrease, right? That's this is going to get smaller. This whole thing is going to get smaller as t gets bigger. So the oscillations are going to damp out. So it's going to end up looking something like a different color for the actual plot. So we'll get some sort of exponential damping. Something like this. Where I can draw some sort of envelope to this thing, which is going to be an exponential decay. Looks like e to the minus gamma t. So that's what this is describing. Which is pretty cool. And so the thing about this is, yeah, we could have guessed this solution and then plugged it into our differential equation, found things, but I mean, this having this exponential factor out front seems like a fairly inspired guess. We would have to essentially know the answer first. Whereas with what we did, while it may have looked complicated in some steps, whatever, nothing about it was particularly crazy. We didn't go make any jumps in logic or anything. We essentially just, plugged something in, turned a crank, and we got this answer out. And in fact, we don't even just have to get oscillations out. So what we can look at is the case, the other cases where beta is greater than or equal to square root of km. So in this case, when I write down my solutions for omega, I still get the I gamma term, but this is plus or minus the square root of 4km minus beta squared over 2m. Now, this square root term is going to be negative, or 0 or negative, whichever one. If beta is greater than 2 square root of m, it's going to be negative. If it's equal to, it's going to be 0. So what I'm going to do is I'm going to factor out a factor of square root of minus 1, right? Which, of course, is just I. So that this becomes I gamma plus or minus square root of beta squared minus 4km, factor of I out front, over 2m. And now I'm going to define some capital gamma, big gamma, which is just essentially very similar to what I called big omega earlier, m, so that I can rewrite omega plus or minus equals I gamma plus or minus big gamma. Now, in this case, we do the exact same thing. We get these delta functions, we integrate the delta functions, so on and so forth, except now I get something which is only exponential decay. So I have a e to the minus gamma, gamma, do I want to do gamma plus or gamma minus here first? Sorry, I'm just trying to decide which one I want to do first. I think I'll do gamma minus, big gamma t, plus, oops, b, e to the minus gamma plus gamma t. So now we only have exponential decay. So this is another interesting case. We don't have oscillations anymore. It's just killed off exponentially. And in fact, in the case where gamma is greater than 0, you see that this first term is greater than gamma. The second term here is less than gamma, which means that this second term, in the case where big gamma is greater than 0, the second term is going to die off faster than in the case where gamma is equal to 0, and the second term is going to die off slower than the case where big gamma is equal to 0. So what ends up happening is that the motion actually ends up being dominated by this term. Since they're summed, the second term is going to die off quickly. This first term is going to hang around longer. So what you'll see is that actually when gamma is greater, big gamma is greater than 0, it takes longer for the system to decay back to 0. So the three cases that we've talked about they all have names. Beta less than 2 square root of km. This is known as underdamped, because you have these oscillations that are eventually killed off, but you're bouncing back and forth still, so you're not damping things out enough. There's the case where beta equals 2 square root of km. This is critically damped. And then beta greater than. I'm sure you can guess what we call this. This is the case where it's overdamped. In both of these cases, you get no oscillation. Whereas in this case, you do get oscillation. And I do see the question in chat. I'm going to show some plots real quick, and then I'll take a second to answer question. So what do these look like? What do these three cases look like? I'll just go ahead and show some quick plots of them. Actually, I'll show 4 cases. The first case here is the dashed line, which is just standard, just undamped, undriven oscillations, standard harmonic oscillator. The red line is underdamped, right? So you see these oscillations happening, but eventually killed off, right? You see them getting, the amplitudes getting smaller and smaller, even though you still have oscillation. The blue line is critically damped, and then the solid white line is overdamped. And you see that both of these, so the critically damped, I should say that this, all of these plots essentially start with the mass at essentially the relaxed point of the spring, and then I give it some kick. So you see that in the critically damped case, I get that initial kick, and then it just exponentially decays back down to 0. Whereas the overdamped case, it gets that initial kick, but it takes longer for it to get back down to 0. Okay. Excellent. So here I'll take a break, see if there are questions. I do see Rashid's question. Can you please explain again the logic behind using the delta function for I when omega equals omega plus or minus? Yeah, I mean it's fairly, yeah, it's just the logic of where are we? Where am I? What am I looking for here? So the question is essentially, if I'm understanding it correctly, why do I choose this form of x tilde? And the logic is just that I have to satisfy this equation here, right? This is my equation of motion. I have to satisfy it. There are only 2 possible values of omega that do satisfy that. And so I'm going to choose my equation or expression for x tilde to just pick out those 2 values of omega, right? I can't do anything else with x. So x should be some function of omega, but I can't make omega arbitrary, right? Because it has to satisfy this. I have to pick out those 2 values, and the way to do that is just with the Dirac delta function. Hopefully that makes sense. Another way of seeing it, another way of viewing it, if you, I don't know if you're more on the mathematical side of looking at things or more on the sort of physical side of looking at things, but more physically looking at this, I can say that, well, this should be the form of my of x tilde, because I know that only 2 values of omega contribute, right? I can only have 2 values of omega contribute, so I should only allow those 2 values of omega. And chi at omega plus or minus constant and not a delta function. Okay, so this is probably getting into these questions of integrability and stuff like that, right? Because so the delta function makes sense to put into an integral. I can put a delta function into an integral, and it makes sense to do so. If I were to just define, x tilde to be some piecewise function where, it's a at omega equals omega plus, it's b at omega equals omega minus, and it's 0 everywhere else, then this gets a little bit iffy as to whether or not this is actually, if I can do these integrals, right? Because x is now no longer smooth over my range. And at the end of the day, this is essentially what we're doing with these delta functions anyway. It's just that when we do it with the delta functions, we're essentially guaranteed to be able to actually integrate this thing to get back to our Fourier, or to do these Fourier transformations. Hopefully that's satisfying for you. I know that might not be the most satisfying answer, but okay. And here's another way of looking at it: is you could just go backwards. We know the solution already. We know that the solution is going to be going to look like this, right? Which we could find by just solving the differential equation. And so we could work backwards and say, okay, I know the Fourier transform of this is just delta functions. So that's not as satisfying of an answer, and I fully recognize that. But that's another way of seeing that this has to be in terms of delta functions. Yeah, it is a very good question. I think that just sort of at the end of the day, we want to make sure that we can actually do these integrals. Okay, I'm not seeing any other questions showing up. So we'll go ahead and move along. Yeah, I'll think about it as well. Hopefully I'll eventually come up with a more satisfactory answer, because I'm sure that that's not completely satisfying for you, but hopefully it's enough to kind of chew on for a bit. Okay, so now let's go ahead and do the even more interesting case, where we now have a driving force. Put it in some force field that acts on this in some non-trivial way. So we'll choose one just for now, which is easier to deal with. So we'll choose our driving force to be something like, I'll call it C. Actually, I don't like the name C. I'll call it F naught cosine omega prime t, where F naught and omega prime are just constants. Those are just values that I fixed to define this force. Okay, so now I want to find the Fourier transform of this. So I want to find f tilde of omega. I know that this is 1 over 2 pi times integral over t of f naught cosine omega prime t e to the minus I omega t. This is actually a pretty straightforward integral to do, and to see why, or to see how, we'll split up the cosine. So cosine theta is equal to e to the I theta plus e to the minus I theta over 2. Write it in terms of exponentials, so that I get something like, pull out the constant, pi. And I get two terms. One which is e to the minus I omega minus omega prime t plus e to the minus I omega plus omega prime t. But we know that this integral t e to the minus I, specifically 1 over 2 pi. I forgot a factor of 2 here. Whatever this may be, omega minus omega prime t. This is just my delta function. This is what we defined it, or this is what we found the definition of the delta function had to be in order to essentially make sure that Fourier, I'll write it in this fancy way, the Fourier transform of an inverse Fourier transform f of x is equal to f of x, right? This was how we found this Dirac delta function. That we took the Fourier transform of an inverse Fourier transform, and that should give us the same thing that we started with. But so, using that, I can see that this is just going to be f naught over 2 times delta omega minus omega prime plus delta omega plus omega prime. So I found my Fourier transform of my force, or my driving force. So now it's just a matter of plugging this into my differential equation, or I guess now my algebraic equation. So I get something which looks like this, plus I beta omega plus k x tilde omega. And this is f naught over 2 delta omega minus omega prime plus delta omega plus omega prime. Okay, so now this may, on the surface seem nice and simple. We just divide the stuff on the right by this stuff, and we have our function of x. But we have to be a little bit careful here. There's a little nuance to this. And it's the fact that we know immediately that the left-hand side, there's a function I can choose for x so that the left-hand side is always 0, no matter what. Right, and that's what we just found earlier. Actually, I'll put a little space here. Right, I know that if I choose this value, or this function for x, minus omega minus, right, where this omega plus minus is all this I beta plus square root of 4km minus beta squared, all this nonsense for 2m. I know that if I plug this in for omega tilde, I always get 0 on the left-hand side. Which means, so I'm going to call this x sub h. I'm going to call this give it the name of the homogeneous solution. So call it x sub h. So I know that if I have some x tilde omega, or say I have a particular solution, which in this particular case, I'll say this is f tilde omega. Doesn't matter what the driving force is. I have something like this plus I beta omega plus k, right? This also solves this differential equation, or in this case, algebraic equation. It solves this equation. But I know that since the homogeneous equation always gives me 0, I can always construct a total solution, which is going to be this homogeneous solution plus the particular solution. Okay? This has to be the case. And there's one very, very simple way of seeing that this has to be the case. So if I ignore the homogeneous solution and I just look at the particular solutions, I'll write down what these homogeneous solution, and this is the particular solution. So say I neglect the homogeneous solution, I just deal with the particular solution. Now, the particular solution does not have any free constants, right? I fix, so beta's a value of my system, m's a value of my system, k's a value in my system. I choose f and omega prime to define my forcing function. I have nothing free. I can't tweak anything, which means that if I just look at my particular solution here, I can't match onto boundary conditions. So you know there has to be something else. It's a second order differential equation. I should have two free constants that I can match to boundary conditions. And what do you know? The homogeneous solution always comes with two free constants. So that's another way of seeing that I absolutely have to include the homogeneous solution into this. Okay, so with all of that said, I'll write out, I'll write all of this out. I can write this function of omega. It's going to be a not particularly pretty expression, but my omega minus plus f naught over 2, right? This is my particular solution, which in this case, we just write in terms of these delta functions, plus delta omega plus omega prime, divided by all of my stuff in the denominator, I beta omega plus k. Okay, so that's a lot, and it's a little bit complicated, but the nice thing, and part of the reason why I wanted to choose a sinusoidal driving function, is everything's in terms of delta functions, which means that this is actually a pretty easy thing to integrate. We've already seen what happens to the homogeneous solution when we integrate it, so if I just look at the particular part, the particular xp of t, so the particular solution in the time domain, just doing these integrals, I'm not going to bore you too much with the details of writing out all of these integrals over and over again, but I get something omega prime squared plus I beta omega prime plus k, right? Delta function here just picks out omega prime. And then the delta function over here is going to pick out minus omega prime. So basically get the same thing here, but with minus omega prime instead of omega prime. So I get minus omega prime squared minus I beta omega prime plus k. And if you go through the effort of simplifying all of this, you get something which looks like f naught times k minus m omega prime squared cosine omega prime t plus beta, right? Our eyes glaze over at this point because it's just simplifying complex exponentials in terms of sines and cosines, but it's useful to, it's a more useful form. So this is our particular solution. Looks horrible. Yeah, doesn't look nice. But now we add it to our homogeneous solution, and we get something that looks like e to the minus gamma t, right, where this gamma is just this beta over 2m, how fast this is decaying. A cosine omega t plus b sine omega t plus all this nastiness, f naught k minus m omega prime squared cosine omega prime t plus beta omega prime sine omega prime t over k minus m omega prime squared. Okay, and now that we're exhausted from writing all this stuff out, we have a solution, right? We have our solution as a function of time, which we of course can match onto boundary conditions and all that. And again, I just want to sort of reiterate, yes, this looks horrible. The algebra was disgusting to get here, all that stuff. But again, none of it was particularly difficult to get to, right? Each step was, picking out specific values of omega with delta functions. It was, the hardest part about this is simplifying exponentials in terms of sines and cosines. And we get this, solution, which is surprisingly complex. And just to sort of give you a visual of the complexity of all this stuff, let's say that we get rid of the damping force, right? The damping force adds a whole layer of complication. So let's look at the case where beta equals 0, which means that gamma equals 0 and omega equals just square root of k over m, which I'll call omega naught. I'll say is the natural frequency. Of the system. So if there was no force being applied, this is the frequency that it would want to oscillate at. And so now, just sort of looking at all this stuff that I wrote up here, I can simplify that down and get something like a cosine omega naught t plus b sine omega naught t plus f naught over m omega naught squared minus omega prime squared cosine omega prime t. So in this case, where we have no damping, we see sort of a competition. There's a competition between the natural frequency, so the oscillation that this wants to go at, right? So here's what the system would want to do if there was no force. And then we have some interfering or competing oscillations going at omega prime, which come from this forcing function. And what we also see is that down here in the denominator, we have omega naught minus omega prime, both squared. Which means that as I bring omega prime closer and closer to omega naught, this coefficient here is going to get larger and larger, right? This is essentially the amplitude of the contributions from the driving force. So as I bring this this driving frequency closer and closer to the natural frequency of the spring, this driving force becomes more and more relevant. And in particular, you see that it blows up when omega naught equals omega prime. And this is what's known as resonance, where, you get sort of this uncontrolled growing oscillation when you drive something at its natural frequency, when you drive a system at its natural frequency. So this is the idea behind, say, breaking a wine glass with your voice, right? If you find the natural frequency of the wine glass, and then you sing at just that right frequency, right? Your I mean, your voice is just sound waves. And so the sound waves create some driving force in the wine glass. And eventually, the oscillations of the wine glass get so large that it shatters. It overcomes the actual, what the strength of the glass can hold, and it shatters. It's also idea of, I believe, Tesla's death machine, where you put very large explosives on either side of the Earth, and you detonate them at exactly the resonant frequency of the Earth, and you can, eventually blow the Earth apart with it. But so just to kind of show this, I have some extra plots here. So here is the first case where the driving frequency is half the natural frequency of the spring mass system. And you can see in this case, it's not super affected. The spring isn't super affected by the driving force. You see these little dips happening up top, but aside from that, nothing major is going on. Then I bring the natural frequency, or the driving frequency, closer to the natural frequency. So here it's, I don't know if you can read this, but it's 0.96. The driving frequency is 0.96 times the natural frequency. And here you really see this competition between the two. So, the driving force will really start to interfere with the oscillations from just the spring, and it'll drive the amplitudes very far down, and then it'll go back up and back down. And so you see this large effect starting to appear when I start getting the driving frequency close to the natural frequency. And then we have resonance. This is the driving frequency exactly on resonance. So the driving frequency is exactly equal to the natural frequency of the system. And you see that there's this just uncontrolled growth of oscillations. They get bigger and bigger and bigger and bigger as you go. And so this, I should tell you what the initial conditions of all of these are. The initial conditions are I pull this mass out to whatever this might be, maybe 1 meter, 1 centimeter, whatever you want to call it, and I just let it go. So I don't give it any initial kicks or anything like that. And you see that since the two frequencies match up, it just by 100 seconds or whatever this time scale is, I'm now 10 times greater. The amplitude is 10 times greater than I started with. So, yeah, that's the idea behind resonance. Okay. So now I'll take a quick pause, hopefully answer some questions. I see a question, what's the best physics problem book? Ooh, that probably is going to depend on what area of physics you're looking for. I mean, I'll say I don't know many books just for physics problems, but, textbooks for classical mechanics, I always use Taylor, E&M, there's, Griffiths is the classic, Jackson if you want something more difficult. If you want to go crazy, you could go to Landau. But these are all textbooks, so if you want just something that's a problem book, exactly. I don't know where I have it right now, but here we go. So I have previously used these Schaum's, SCHAUM, Schaum's outlines to learn stuff. They're little cheap books, but they have a lot of problems, material in them. Okay, so the amplitudes seem to grow exponentially in the case of resonance. Can you describe it using the solution you have obtained? It actually, so the growth, I don't believe, is exponential. I believe it's actually linear in this case. And one way, so without getting, I don't know how deep you want to get into this, but so if you match onto the boundary conditions where x of 0 equals 1, x dot 0 equals 0, you get something like 1 minus, what is it, f naught over m times omega naught squared. Essentially, you just have to solve for the boundary conditions. And so the reason why it doesn't immediately explode is because you have this other factor as well, omega prime squared. And so you can look at the limit of this guy, and you'll see how it grows. Except I think it'll be a bit complicated, but I don't think it's quite exponential. I actually think it's linear growth. You know, it starts out very quick, but then it sort of reaches, I think, a steady state. I'm not 100% sure on if it is true linear growth or not. But yeah, so the way to do it would essentially be taking this limit, right? Which I'm assuming you could do with L'Hopital's rule, all that stuff. If that floats your boat. Right, because I can rewrite this as cosine omega naught t f naught cosine omega naught t plus cosine omega prime, minus prime t over omega naught squared minus omega prime squared. So now I want to take the limit as omega naught goes to omega prime. And yeah, you can see that it's indeterminate, so you can use L'Hopital's. And probably get, yeah. So, sorry, I'm trying to think about this. I think that you would just get linear. Yeah, right, because I take a derivative with respect to omega naught, and I get a factor of t out front, right? And then in the bottom, I just get omega naught minus omega prime squared, so now I take the limit, and I get something linear in time. Hopefully that makes sense. Okay, excellent. So now, I want to just show another quick example of how this can be used to, really quickly solve some differential equation. And to do that, I'm going to go back to the wave equation. I know I said that I would be talking about this outside of the context of the wave equation, but I only partially lied. So we have our one-dimensional wave equation, and I know that my solution is going to be a function of position and time, x and t. So now what I'm going to do is I'm just going to rewrite this. I'm going to introduce Fourier transform variables for both x and t. I'll call this, this guy will go to k, and this guy will go to omega. So that I can write this as, now it's going to be a double integral, minus infinity to infinity, k, minus infinity to infinity, d omega, phi tilde, k, omega, I, k, x, e to the I, omega t. right? Okay, so now I just do the same thing that I did before. I take derivatives. I know that my derivatives get replaced with I times whatever the respective conjugate variable is. And I find that this equation just becomes minus integral minus infinity, the minus coming from I squared again, d omega, a, d omega, omega squared, phi tilde, a omega, e to the I kx, e to the I omega t. And this is minus very similar thing. Omega a squared, c squared, c squared, phi tilde, a omega, and then my exponentials, e to the I omega t. So again, I can, however you want to see this, you can see it as inverse Fourier transforming, you can see it as, you know, these integrals and exponentials are the same on both sides of the equation, so I'm just going to look at what's inside of the equation. I'm going to rearrange some stuff, and I'm going to get omega squared minus c squared k squared, omega tilde, k omega equals 0. And so we have a very similar setup to what we found before with just the regular harmonic oscillator. And actually, you can see that this looks almost exactly like the harmonic oscillator. And that's actually no coincidence. There is something very, very deep going on with that, but that's a little bit beyond the scope of what I want to talk about today. The important thing is that this exactly reproduces our dispersion relation, right? This tells me that I have to require omega squared equals c squared, a squared. So again, just like before, I can write my solution for phi in terms of delta functions. But this time, the coefficients aren't just going to be constants, right? I'm not, this only solves for one of my variables. I'll say I'm solving for omega, which means I can still have some non-trivial dependence on k, right? K can be whatever I want. I just have to fix omega so that it obeys this dispersion relation. And so I'll do that just with delta functions minus ck plus g of k delta omega plus ck, right? Because I have a positive and a negative solution once I take the square root. Okay, so now I just do the inverse Fourier transform of this, right? So I just say phi of x comma t is equal to integral minus infinity to infinity a the omega f of k delta omega minus ck plus g of k delta omega plus ck, and then my exponentials, e to the I kx, e to the I omega t. Now, just like before, I can use the delta functions to collapse one of my integrals. I can't collapse both of them, but I can collapse one of them. I'll choose to collapse omega, and I'll just pick out in each term, a single value of omega. First term, it's going to be ck. The second term, it's going to be minus ck. So this ends up being something like this. F of k, e to the I k, x plus ct, plus g of k, e to the I k, x minus ct. Okay, so now I'm going to rewrite this in, it might look like a funny way, But I'm going to just rewrite this using two different quote-unquote coordinates. I'll write this as a f of k e to the I k psi plus gk e to the I k eta, where I just defined psi is x plus ct and eta equals x minus ct. Okay? Now, if I were to look at each, so forget sort of anything physical. Let's just look at the mathematical expression here. So forget that we're dealing with time and space and all of that stuff. If I were to just look at this, right? So dk fk e to the I k psi. So if I know, so say f and little f are Fourier transform pairs, then I know that this is just going to be f of psi. Right? That's all there is to this. This is just a Fourier transform, or an inverse Fourier transform, whichever one. Right? And similar for g. So if I allow, I shouldn't erase that up here. Psi equals x plus ct, eta equals x minus ct. So, and I'll say that f and big F are Fourier transform pairs, and little g, I don't know if you can see that. Actually, let me move that. So I'll say little f and big F are Fourier transform pairs, and little g and big G are Fourier transform pairs. Then over here, I just get little f of psi plus little g beta. Right? All I'm doing is a Fourier transform. I know that these are the Fourier transform pair functions corresponding to f and g. Which means that I now have my solution to the wave equation, my general solution to the wave equation, is just f of x plus ct plus g of x minus ct. Exactly what we found before, but arguably in a faster way, and perhaps a more intuitive way that we just, Fourier transform. Again, just Fourier transform, turn the crank, and you get your solution, rather than having to guess anything, decompose into basis function, things like that. So just a pretty cool reproduction of a known result that we able to do with just Fourier transforms. Okay, so now I want to make a comment. This is all great. This is all fantastic. Oh, Fourier transforms are magic. They do everything for us. Not quite. Unfortunately, I've sort of cherry-picked examples that are very easy, very, very straightforward to do. Cases where, the inverse Fourier transform is, the integral is easy to do. It's just delta functions, for example. Cases like this, where essentially by just choosing our variables in a combination, which is smart, we just get another Fourier transform. This isn't always going to be the case, so we can't always use Fourier transforms and have some nice, neat solution. And so I wanna sort of go on this while we're on this train of the wave equation. I want to show this with an example. And I'm going to take the wave equation. I'm going to modify it slightly by dx squared by just adding this term here. So it's another term proportional to phi. This is all linear in phi. I just have this extra term with some constant. In general, this is known as the Klein-Gordon equation. And it essentially describes a very similar thing to the wave equation, but with some quote-unquote mass term. All this. Okay, so again, I do the same thing as before. I'm going to skip some steps because we've seen this sort of over and over again. I'm going to Fourier transform both x and t, get omega and k, and I get something which looks like omega minus c squared, a squared, minus m squared, phi tilde of k omega, that's equal to 0. So again, I do the exact same thing. I pick out my this should be omega squared, sorry. I pick out my solutions for omega and I rewrite phi in terms of these. But now you see that these are going to be a little more complicated. Delta k minus square root of c squared k squared plus m squared. G of k delta k minus square root of c squared k squared plus m squared. Those shouldn't be k, sorry. Those should definitely be omega. Okay, so now I'm sure you're saying, okay, how does this change anything? We still just have delta functions. Who cares? Big deal. We just collapse an integral and we're good to go. Okay, well, let's do it. Let's rewrite phi of x comma t in terms of this integral, and hopefully I don't have to write this all out explicitly. I'll skip down to after we've collapsed the integral over omega, and I get something like f of k, my exponential, and I get ikx plus I square root of c squared k squared plus m squared, all of this times t, plus, write it down here, ikx minus I square root of c squared k squared plus m squared times t. Okay. Now, you see that we can't just do the same thing as we did before. We can't just, say, okay, this is just a Fourier transform, yada, 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 because we have this weird square root thing to deal with. Now, I'm not going to get into like solving this or anything like that because it's very difficult. This is a very difficult thing to solve. But this is just sort of to show you that, just because you can take the Fourier transform doesn't guarantee you an easier problem. There are specific cases where it does. But this is a great example of, yeah, I can get to this point, and great. I get a dispersion relation. I got almost to an expression that works, but here I kind of get stuck. So just keep that in mind before, you say Fourier transforms are the saviors of all differential equations. Okay, and so I want to do one last thing, but I'll take a quick break. I need to drink some water, answer any questions people may have, so on and so forth. Okay. I'm not seeing any burning questions showing up in chat. So I guess I'll go ahead and get on to this last example. And this will be an example of, we're gonna do a few things with this. The first thing is to show, again, this idea of, okay, Fourier transforms, well, in some cases, I've hyped them up as being this great thing that just, spits out your answer and they're super easy. They're not. In principle, they're not. In principle, they're very straightforward, but in practice, they can be very challenging to deal with. And so, to sort of showcase that and also see a very interesting result that we'll end up using later on when we talk about quantum mechanics, I'm going to talk about a Gaussian. So Gaussian function, f of x equals a exponential minus x squared over 2 sigma x squared. So if I don't know how familiar people are with this sort of function, but it's what many people refer to as a bell curve. So in this particular case, I have x, I have f of x, and it's going to look different color here. It's going to look something like that. Assume that it's symmetric and all that stuff. Assume that my artistic abilities are better than they actually are. So it's this bell curve, and the sigma x, it's some characteristic width. It essentially tells us how wide this Gaussian function is. So if I make sigma x, I believe if I make it bigger, then this thing's gonna flatten out more and get wider. So it might look green. So it might end up looking something more like that. So a little bit flatter but fatter. And then if I make sigma x smaller, my function might look something more like this. A bit more narrow, but taller. Okay, so that's what sigma x is. It's the width of this Gaussian or bell curve, whatever you want to call it. Okay, so now I want to take a Fourier transform of this. And this is just a math exercise, right? There is a physical application to all this stuff, but for right now, I just want to look at the mathematical exercise of going through and taking this Fourier transform. So I know that this is going to be something like 1 over 2 pi integral minus infinity to infinity f of x e to the minus I k x, and just writing all this stuff in. Minus infinity to infinity dx x minus x squared over 2 sigma x minus I k x. Okay, so that's our Fourier transform for the Gaussian function. Now, this is a bit tricky. This is a bit of a tricky integral to do, but we can do it. So right now, it's not immediately obvious how. The first thing that we have to do is simplify whatever's going on in here. And in fact, if we could just make it something like a variable squared or whatever, just a single value. This x squared plus something times x nonsense is a bit annoying. So what we'll do is complete the square. And so essentially, for those that don't know necessarily what that means, just means that we're going to take the argument that's in there. Sorry, I think this should be sigma squared. IKX, and we want to rewrite it in some form where we have x plus b squared plus c, right? Where a, b, and c are all constants. These are all just some number. They don't depend on x. The only dependence on x is here. So I can expand this out, and I get something like this, plus 2abx plus c. And now I just solve for a, b, and c. I match coefficients. Whoops. Oh, sorry. This should be a times b squared plus c. I match coefficients of powers of x, and I find, without wasting your time with a whole bunch of tedious algebra, I get something that looks like this. B is equal to ik sigma x squared. And then c is equal to minus k squared sigma x squared over 2. Okay. So, and this all might seem very unmotivated. It's and I get that. But these are sort of tricks that you should sort of have in your back pocket. These completing the square tricks, all of that, and you'll see why why we're doing this completing the square business in a second. But this sort of technique is used quite frequently, actually, and part of the reason I want to look at this integral in particular is because these sorts of integrals show up everywhere in physics. We get them all the time. Sigma x. I actually don't think this should be squared. That should not be squared. Minus sigma x squared over 2. Okay. Excellent. So now what I can do is here I have x plus a constant, right? Which means that I can just shift it. I can just shift x. So if I take x to x minus ik sigma x, right? The dx doesn't change because this is all constant with respect to x. My bounds technically change, but I'm going to ignore that for the time being because it ends up being that any imaginary part that you add, since this diverges or this goes to infinity, each of these bounds go to infinity, that the imaginary part's killed off. It's killed off by taking these bounds to infinity. So actually this imaginary part isn't going to show up in the bounds. But so I'm just going to make this shift, right? And all it's going to do, the only effect that it's going to have, is it's going to take this x plus ik sigma to just x. So I get something which looks like this, over 2 pi. And I can also, since this has absolutely no factors of x in it, I can just pull it out of the integral altogether. So I get something like a squared sigma x squared over 2 integral minus infinity to infinity dx minus x squared over 2 sigma x squared. And actually, this whole business is, we could stop here if we wanted to, right? We have our dependence on k. This integral is going to be some constant. But I do want to actually go through solving this integral because it's one of those tricky things, and this integral is a very, very important integral. I think it should be sigma squared in b. Yeah, I had it as in one place sigma squared, in one place it was not squared, but let's see. A is correct. B should be ik. Yes, it should be squared. Thank you. Appreciate it. Okay. Perfect. So I want to go through solving this integral. I'm just going to call this integral I, just because, like I said, it's a good exercise to do, and it's an important integral to know. So again, this is a bit of an inspired guess. We might be able to arrive at this because of the fact that we have an x squared up here. But what we're going to do is we're going to instead look at the square of the integral. So when we square the integral, we get something like dx x minus x squared over 2 sigma x squared. Integral minus infinity to infinity dy x minus y squared over 2 sigma x squared. And I knew somebody was going to ask me why I didn't change these integrals. I can talk about it a little bit more after this. I want to get through this example first, but the basic idea is that when I take the real parts of this this integral to infinity, it kills off any imaginary shift to the bounds. So since this is an imaginary shift, or I guess in general a complex shift, but the real parts is completely insignificant since I'm already taking this to infinity, any complex shift is also killed off. And I can write a little bit more about that later on if you're still bothered by it, but I want to get through this real quickly first. But so I can write the square of this integral as dx integral dy x minus x squared plus y squared over 2 sigma x squared, right? Because I mean this integral here isn't going to see anything having to do with x, and this integral here isn't going to see anything having to do with y, so I can just sort of smush the exponentials together. So now what I do is I shift my coordinates, or I change my coordinates. So instead of working in x and y, I work in x equals r cosine phi and y equals r sine phi. So I shift to polar coordinates. Okay? Now, I've talked about this before in these streams, and when I have my area element, my differential area element, dx dy, in Cartesian coordinates, and I shift to polar coordinates, this becomes r dr d phi. And essentially the quick and dirty explanation of that, if you don't remember, is I have some small box, right? I'm summing over all of these boxes that make up my space. I can do that in polar coordinates, right? Polar coordinates are going to be described by some r and some phi here. And my, I'll write it a little bit more curved. In this case, clearly this part is dr, right? The part that shifts in the radial direction is dr. But in the rotational direction, in the phi direction, it's not just d phi, right? If I have some arc of a circle, right, I can trace out the same angle, but it gets longer as I move out, and it gets longer proportional to r. So this is actually r d phi, hence why this r shows up here. So all that said and done, I write x squared plus y squared is just r squared. And so the square of my integral is, I'm going over all of my two-dimensional space, So 0 to 2 pi for d phi, 0 to infinity for r. I have to include that this factor of r here. Minus r squared over 2 sigma x squared. Okay. This integral is super easy to do. We can do it immediately without even thinking, right? It just gives us 2 pi since nothing depends on phi. So this is 2 pi integral from 0 to infinity dr r x r squared over 2 minus sigma x squared. So now we just change our integration variable. Do a u substitution, as I call it. I'll plug in u equals r squared, which means that r dr is 1/2 du, right? R dr shows up there, so I just plug in 1/2 du there, and I get something like just pi, because of the 1/2 kills this too. Integral from 0 to infinity, right? 0 for u is still 0, and then infinity is still infinity. Du x minus u over 2 sigma x squared. This is about the easiest integral that we can do. And when we do it, we get 2 pi sigma x squared. So, our actual integral that we cared about is the square root of this. It's just this guy. And our Fourier transformed Gaussian expression is going to just be a times sigma x over square root of 2 pi x minus k squared sigma x squared over 2. So what is this? If we look at this, so remember this here is a function of k. And now if we go all the way back up and compare here, right? Our Gaussian was defined essentially as an exponential of minus something squared. So it's a constant times something squared. So what we see is that when we take a Fourier transform of a Gaussian, we get another Gaussian, right? It's some constant, whatever, I don't care about that, times the exponential of minus, you know, all of this stuff is constant, the sigma x and the 2 is a constant, but k squared. So a Fourier transform of a Gaussian is a Gaussian. And in particular, if I'm just going to rewrite this, f of k equals, I don't care, I'll call the constant b, exp minus k squared over 2 sigma k squared, right, where now sigma k is the Gaussian's width in k space. We see that sigma k is equal to 1 over sigma x, or rewriting this, sigma k sigma x is equal to 1. This is an uncertainty relation. And uncertainty relation. What it's telling us is as I make the Gaussian in x narrower, I have to make the Gaussian in k wider. And vice versa. If I make it more narrow in k, I have to make it wider in x. So what this is telling me, so say, you know, I have some statistical distribution described by a Gaussian for where something might land, right? Say I'm dropping a ball, and I have a distribution of where the ball might land. And it's described by a Gaussian. Now, if I then go and look at what k that value that ball might have, I find that if I better know where that ball will land, I don't know as much what k will be when it lands. Right? Does that make sense? So if I know that whatever it may be, so say I know in x a very, very sharp Gaussian like this. I don't know, call this p of x, some probability of x. Then the corresponding probability in k is going to be, let's say p tilde of k. This is going to be wider. And this is the whole idea of an uncertainty relation, right? If I know something better in x space, I know it worse in k space, so on. But I mean, we shouldn't be too surprised by this, right? This idea should actually come as zero surprise to us, because we already saw how if I have x tilde, take just our standard harmonic oscillator, x tilde omega, what frequencies make this up? Well, I found that only two frequencies. I knew very, very well which values of omega made up x. But when I look at it in t, I get some, I guess I should make this down farther. I get an oscillating function, right? And so I get all of these different values of t being, possibly contributing to x of t, whatever. It's the same idea, right? I know that everything is very, very localized in omega over here, but things are very spread out and unlocalized in t here. And this is the general idea behind an uncertainty principle. And so this once we get into quantum mechanics, this shows up again, right? And what we find is that it's not special about quantum mechanics. What's special is that quantum mechanics tells us that position and momentum are Fourier transform pairs of each other. And so, of course, we get an uncertainty relation between them, because uncertainty relations are intrinsic to Fourier transform variables. Same thing with energy and time. Energy and time are also Fourier transform pairs in quantum mechanics. And that is the core of where uncertainty relations come from. The fact that these variables are Fourier transform pairs of each other. There's nothing super secret and mystical going on about it. That's just it. That's all there is to it. But yeah. I think that's sort of all I had today. So if there are any more questions, feel free to ask. I'll hang around for a little bit more, then wrap things up. Okay. No, I actually don't do every Sunday. This is actually the first time I've done it on a Sunday. I usually in the past have done Wednesday evenings, so Eastern time, so in the US, Wednesday evenings, but I wanted to be a little bit more flexible for my my viewers that aren't in, this hemisphere. So I might start doing Sunday. I doubt I'll go to every Sunday. I highly doubt that. But I might switch to Sundays. We'll see. It'll sort of depend on, feedback, what people think, that sort of thing. Yeah. Glad you enjoyed it. That's actually so question was what I'm planning to cover next time. That's a good question. So I haven't done one of these in a while, partially because I'm sort of trying to get a good track of how I want to navigate things. And so actually what I've sort of decided on is where I want to go next is I want to start talking about Hamiltonian mechanics. So I've done a lot with Newtonian mechanics, sort of done this sidetrack with Fourier analysis, wave equation stuff. But I think the next thing I want to get into is Hamiltonian mechanics, because that'll very nicely lead into things. So to sort of get you into my mindset of this, I personally don't like to take things for granted. I don't like to just say, okay, we know these equations work, so this is what we're going to look at. I like to motivate things sort of step by step, so that's sort of what I've been trying to do, and I think that Hamiltonian mechanics are going to be a nice next step. Ah, hello, Narf. Good to see you. Unfortunately, this is the very end. Yeah. Just in time. Yeah, just in time to well, I appreciate that you dropped in to say hi. Yeah. Okay. Well, thank you guys. I think I'm going to wrap it up. I appreciate all the support, all the good questions, all that good stuff. If you're watching after the fact, all of that. Thank you there. Feel free to drop any questions below. Yeah, and again, if you're watching this after the fact, and I see Narf appreciates the Euro friendly time. That's sort of what I'm trying to figure out if this is a better time than my usual Wednesday evening. So okay, well, thank you all again, and I'm gonna wrap things up.